Bonjour. Est-ce que vous m'entendez déjà? Faudrait qu'il y en ait. N'hésitez pas à parler avec le micro, hein. Ce sera fait pour, hein. Donc, ah ben voilà, ça y est, il y a du monde qui arrive. J'allais vous demander justement s'il y avait du monde déjà connecté à 8 heures ou pas. Si tout le monde avait eu la possibilité de se connecter. Donc, je suis désolé hein, de cette organisation un peu au dernier moment. Mais bon, il a fallu décider pour essayer de faire au mieux pour tout le monde. Vous avez eu des nouvelles de votre cours pour l'après-midi? Enfin, de vos cours, enfin vos TD plutôt, c'est du TD que vous avez cet après-midi? Vous êtes à peu près 15, une quinzaine. Il y a 24 enregistrés, je crois, dans le groupe. Ça veut dire qu'il en manque quand même une dizaine. Alors, the link for the English TD is the other one. Yeah, that's the French one. Sorry. There were two links. They finished by the same 09, but they are different. Yeah. Oh, yes, 09.
So can you hear me? Is that good? Can you see the screen? Okay. Apparently everything is going fine. So, okay, we are going for this online class today, and the idea is that we start doing some exercises that are on the lecture notes, and we are trying to have it, let's say, in a normal way, even if it is difficult to do exercises online. However, I suggest you that you go on your lecture notes, the English version, And we start as a first exercise with exercise 1.22. On the French class, I don't remember if you want to go on the French class. Let me see, which kind of exercise is this? So I let you take 5 minutes to digest the text of this exercise, the requirements, and then we try to solve it together. In the meantime, I'm trying to see which exercise is this in the French lecture notes. Okay, this is the English one, and the French one, if you want to see it, and the French version is 1.29. This is the French lecture notes. So here in this exercise, everything goes like this. We have a vector space V2, which is this space of errors. So it contains the usual standard geometric vectors V. And we are saying in this exercise that the basis that we are considering is a basis formed by vectors Bi. And since this is a bidimensional space, it has only 2 dimensions, this set of vector is composed by vector B1 and vector B2. And they're kind of unit vectors. So the text says that they are unit vectors. So the norm of those Bi vectors, it is equal to 1. And the text also says that the angle between those 2 vectors, so let's say that this is, let's make it a little bit bigger. So let's say that this is vector B2, and that vector B1 is norm 1, and it is like this. So the angle phi between the 2, it is 45 degrees, pi over 4, sorry. So this is the configuration. We have a space here around, which is the vector space V2 of geometric vectors. And this is the basis that we are considering. It is unitary, but it is not orthogonal, as you can see. So the first question of the exercise, question A, it is that we want to find what is the dual, find the dual basis Bi up of V2. That's the question. This is the first one. So I'll let you think about it 2 or 3 minutes, and then we go on trying to see how we can find this dual basis. So I see that there is a question here in the chat. There's maybe a little question. Can we find a solution to these exercises somewhere, or will we calculate all of them in the TD? No, it's called TD. We are calculating them here in the TD. There are no answer to the questions at the end of the chapter of the lecture note. There are many exercises inside the body of the lecture note. If you have already seen it, they are solved. They are supposed to help you to go through the solution of the exercises. But clearly, the one that you are supposed to prepare by your own for the TD, it's up to you to prepare them. There is no solution that is given out. It's the work that you are supposed to do. Hope this is clear for everybody. By the way, I suggest that if you have any question, don't write in the chat because it's difficult to me to keep concentrated on the chat. You just unmute yourself and then you pose your question using your voice, using the mic, the microphone. That will be easy, so everybody can hear the answer and the question. So let's try to figure out how to find these dual bases. The idea here is that we can find it in many ways. So the first way we can find it, let's call it this kind of geometrical method. That's very useful because it's very intuitive as any geometrical approach in math. So geometrical method, which is simply based on the duality relation. We have seen in class that the relationship between a dual basis and the basis is what is called the dual relationship, the inner product between Bi and Bj. This is the basis. This is the dual basis. That's simply given by delta Ij. So, by geometric method, we are trying to see what that means. So, let's say that Bi is B1. Let's consider, for example, B1, comma B1. This is equal to 1. And if we consider B1, sorry, if we consider B1, comma B2, sorry, I forgot to put the arrows here, that needs to be equal to 0. What that means? That the vector B1 that we are looking for, which is the vector 1 of the dual basis, needs to be orthogonal to B2. B2 is this vector here. So we know that the vector B1 up that we are looking for must be orthogonal to this. So it must lie on this axis here, the one that I'm drawing right now. Why? Simply because the vector B1 that I'm looking for is orthogonal to B2. And B2 having this direction, that vector needs to lie in this direction here. However, the question is, will that vector be oriented in this direction, or will that vector be oriented in the opposite direction? There are two possibilities. Once the direction is chosen, we have two verse for this vector. So we need to figure out which one of the two is the good one. And since this relation, we use it to tell us that the vector B2, B1 up was perpendicular to B2, then we can use now this relationship that will tell us that the component of vector B1 up that we are looking for with respect to the vector B1 is positive, is 1, which is larger than 0. So the scalar product, the inner product between the arrows B1 and the arrows B1 needs to be positive. That means that the vector that we are looking for will be in this direction, because the component of this vector B1 up here, with respect to B1 down here, it is positive. This direction here, if I take the scalar product with this vector B1, is not positive, that is negative. So I have already found what is the direction of the vector B1, which is only this one. So we are halfway to. We are halfway to. What is the information that we are lacking? The information we are lacking is the norm of B1. So what is the norm? What is the norm of B1? We know the direction, the orientation, but we need to know the norm of B1. And here, clearly, we can put it in this way. What is the norm of B1? So think about it. So the way we go is again exploiting what we have. Out of the duality relationship, we have this relation. We know that B1 up, inner product B1 down, that's going to be equal to 1. But this is an inner product. And we said that the space we are working in is V2, the space of arrows. And that space of arrows has a natural inner product, which is given by the dot product, whose symbol is this one. So the couple, the vector space V2, endowed with the dot product is the Euclidean space that we are considering. So I know that B1 dot B1 is equal to 1. But I know how to calculate the dot product in V2, and that is the norm of B1 that I'm looking for, times the norm of B1 down, times the angle between the two vectors, cos theta. And that needs to be equal to 1 because of the duality relationship. Now you see clearly that I gave you some information in the text. And that information was that B1 was unitary, is 1, the norm of B1. Sorry, I kept forgetting putting the errors. The norm of B1 down, it is 1. And the angle between the two vectors, B1 and B1 up, look here, this is B1, vector B1. And this is B1 up. Now I'm asking, what is the angle theta between the two? What is this angle here? And then you will not have any difficulties in understanding that since this angle here is the complementary of this with respect to pi, so this is phi, the angle theta that I'm looking for is simply cos of pi and a half minus phi. And this needs to be equal to 1. So, at the end of the day, the norm of B1 that we were looking for is simply, this is 1 over square root of 2, so it's square root of 2. This is the final answer. So we have the direction, this one that is marked here. And we have the norm, which is the square root of 2 of this vector. Now, I'll leave you 5 minutes and you'll try to reproduce the same reasoning that I've been carrying on right now in order to find now B2, the second vector of the dual basis. Should be able to go through the answer by trying to understand what I did for vector B1. Then we will do that together. So, how we proceed now? Using, again, as we did before, the duality relation, which is the property that allows to relate the dual basis to the basis of a given space, of a given vector space. And now, instead of considering vector B1, we are considering vector B2. And we are taking the scalar product with B2, and we are taking the scalar product, the inner product of B2 with B1. Again, this is 0, and B2 up, inner product B2 down. That's going to be, sorry, here is a little bit messy. B2 up and B2 down is going to be equal to 1, a positive quantity. So we know that the vector B2 up that we are looking for, that we are searching, it is orthogonal to B1. Now that vector that we are looking for, therefore, will lie on this axis that I'm drawing right now. And again, we need to understand whether that vector B2 that we are looking for is oriented towards the bottom or upwards. Which of the two directions is the good one? We know it because we know that the inner product of B2 with B2 down, with the basis vector B2, the scalar product of the vector that I'm looking for with the vector B2 that I'm now encircling, that needs to be positive. And so, of the two directions, only this one is the good one. So the vector B2 that we are looking for will be something that is like this. So this is the origin, this is B1, and that's B2. So this goes away. That's the vector that we were looking for. This is vector B2, up. If you go through the calculation, as I did as before, you will see easily that the norm of vector B2, it is, norm of vector B2 is again square root of 2. For the same exact reasoning that we did before, which is written here. You need just to replace the index 1, whether it appears up or down in this expression. You replace it with the index 2, and you will come up again with this, the norm of B2. So, just to make a recap, we were given a unit basis, B1 down and B2 down, and we were able to come up with the dual basis, which is this vector here that we call B2 up, and this vector here that we call B1 up. And this was our angle phi between the two vectors. This is the answer to the first question. Now, I'm not satisfied with this answer because it's just one method. I want to show you how we can solve the very same problem with a second method, which is an algebraic method. Geometric is very intuitive, the way we went with the previous method, but unfortunately, it's limited to, let's say, 2 dimensions or even 3 dimensions, if you are good enough to visualize in 3 dimensions. But then it fails when we go to higher dimensions. Suppose you are working in 4 dimensions, that would be not anymore possible, the geometric intuitive way that I solved the problem before. So I want now to approach the problem in a very standard and algebraic way. Less intuition, a little bit more of algebra, a little bit more of calculation. So the idea here is that we are looking for a vector bi up that are members of the dual basis, and I know that I can decompose them on the basis. I decompose them on the basis of the space V2. So that would be the component of the vector bi that I call jth component of vector bi up on the basis of V2, which is bj down. This is simply the linear combination. That would be B1, 1, B1 plus B, let's say I call it I, sorry, not 1. So let's say BI 1, B1 plus BI2, B2, which means that vector B1 up will be written B11, B1 plus B12, B2, and vector B2 that I'm looking for is written as B21, B1 plus B22, B2. So you see, I'm looking for the vectors b1 up and b2 down. And what I really care about is their component. I want to go algebraic, so I need to find what are the 4 components, b11, b12, b21, and b22. Once I know that, I will know exactly what is the vector b1 and b2 up that I'm looking for. So I want you to think a little bit how to find this component, and then I will guide you through the solution. So we are after the component bij. So we are after the jth component of the bi vector. We know how to calculate that. In class, I saw that we have a functional, which is called the bj up functional, which is it in the vector of which you want the component and which spits out the component you are looking for. So bj up will act on the vector bi here and will give you the components that we are looking for. This is the definition. It's the definition of this linear function that we call the vector component functional. And we know that there is a theorem, which is called the Riesz-Frechet theorem, that tell us that this object here, the linear functional bj up, is uniquely associated to a vector bj that lives in V2, such that bj inner product, bi, is the operation that you need to calculate. So this object, the linear functional that we call the component vector, lives in the space that we call V2 star. It is a functional. It lives in the dual space. While this vector here, which is uniquely associated by the Riesz-Frechet theorem to that functional, lives in the vector V2. It is actually the dual basis that we are looking for. This is the dual basis that we are looking for. This is from the fundamental point of view of theory. Now, we have our B1 up and B2 up that you see here. These are the expression of B1 up, B2 up. So now we use the duality relationship as before. Use duality relation to find the components of Bi. That I remember, this is living in V2. It's not in the dual space. This is the dual basis of the standard space. So duality, again, Bi up, Bj down is simply equal to delta Ij. I up, there is a pairing of this index, I up, and the pairing of the index there. So let's calculate. We have that B1 up, B1 down is equal to what? Is equal to the expression that we have of B1, which is written here. You see here, this is B11, B1 plus B12, B2, and then I need to take the comma with B1. And that needs to be equal to 1, according to the duality relationship. Then we will have B1, sorry, again, forgetting the arrows. Then we have B1 up, comma B2 down. And again, that will be B11, B1 plus B12, B2. And now we are taking the inner product, the dot product, with 2. But now, since here I have an index 1, I is index 1, and J here is index 2, B1 delta 1, 2 is equal to 0. And so I have that this must be equal to 0. Then you can keep going on. Then we have B2 that we are needing to dot product with B1. So B2, B1. That would be, what is the expression of B2 is written over there. B2 is B21, B1 plus B22, B2 down, comma, B1 vector. Again, this is B2, B1. Here we have an index 2, here we have an index 1, and so that will be 0. And finally, we will have B2, comma, B2. I'm not going to write it again, but then you understand that this will be equal to 1. These are the algebraic relationship that will give us what we're looking for. So let's try to solve the first one. The first one will be, this is an inner product. It's a real dot product. So that's our inner product. So we can throw out the B11 from the parentheses, and we will have that this is equal to, the first relationship is B11, and then we have B1, comma, B1, plus B12, and then we have B2, comma, B1. And this needs to be equal to 1. And then from the second, we have B11, and then we have B1, comma, B2, plus B12, and then we will have B2, comma, B2. And that will be equal to 0. And then you write the other expression that are missing here. I will not write them. It's up to you to find them. So let's go on. We will have B11, and now I'm asking you, what's the value of B1 star, what's the value of B1, of B1 comma B1? I'm trying to calculate this quantity here. That you know. It is the dot product between two unit vectors that are collinear, that is equal to 1. Remember that these problems, the basis B1 down, Bi down, sorry, it is a unit basis plus B1, 2, and then we have B2 comma B1. That's the norm of B2 times the norm of B1 times the cosine of the angle between the two. Just remember, I'm going up, the angle between vector B2 and vector B1 is this angle phi that you're looking here. So that will be cos phi, and phi was cos pi over 4. And that needs to be equal to 1. Then we look at the second line in this series of equations. And the second line is B1, 1. And then we need to evaluate with what is B1 dot B2. But that evaluate to 0. That's time 0. Plus, then we have B1, 2. That is B2 comma B2. Again, that is equal to 1. Sorry. I'm making a stupid mistake here. B1 you got B2 is not orthogonal. That is cos phi. Forgot. Cos pi over 4. Plus, again, here B1, 2, and that was 1. And that needs to 0. So, I leave you to calculate the other relationship. At the end of the day, you will have 4 equations for the 4 unknown, for the 4 unknowns, B11, B12, B21, and B22. Since the system is linear, you can solve it and you can find easily that we have B11 equal to 2, B12 is equal to square root minus square root of 2, B21 is equal to minus square root of 2, and B22 is equal to 2. So if I put everything together, B1 will be equal to twice B1 minus square root of 2 B2. And B2 will be equal to minus square root of 2 B1 plus 2 B2. This is the formal algebraic solution to the problem. This is a vector, B1 and B2 up, that have the norm of square root of 2 and the orientation that is given here, that is given in this plot that you are seeing here on the screen. However, that's not clearly obvious, because what I'm giving here is the vector B1 up, B2 up. I'm giving you the dual basis in terms of their components with respect to the basis. But probably you are most used to see them in terms of the orthonormal basis, the orthogonal basis EI. So let's find the components of bi up with respect to an orthonormal basis. We have a special labeling, special notation for the orthonormal basis, and that is E hat I. That's the spatial symbol. A hat means that the basis has unit norm, and the letter E means that it is orthogonal. So it has two properties. It is orthogonal and it is normal. So how we can find that? It's simply, we need to express the basis vector bi. Those are the basis vector in terms of our EI. And so we will have it as component bi j ej. This is simply given by vector b1 will be equal to, will be equal to b1 1 e1 plus b2, sorry, that's b1 2 e2. And vector b2 of the basis will be equal to b2 component 1 with respect to the orthonormal basis plus vector b2 component 2 with respect to the orthonormal basis. So let me move this so I can keep going on. So let's evaluate the first. I'm asking you, this is vector b2. This is vector b1. And I'm asking you, if I give you this new basis, which is e2 hat and e1 hat, which is the basis that you see here with the dashed line. This is e1, and that is the basis e2 hat. Now I'm asking you, what is the component of b1 with respect to e1? And that is simply equal to e1, since b1 is norm 1. And then what is the component of b1, which is this vector here, with respect to e2? And see, they are perpendicular, and so that is plus 0. So this is simply e1. Let's go now to understand what is the component with respect to e1, with respect to this basis vector of the vector b2. And you will see that that is cos phi e1. And then immediately that would be sine phi e2. So the vector b1 will be equal to e1 hat, and the vector b2 will be equal to square root. Now, remember, we started from this relationship here. We had b1 up as a function of the basis of b2, b1 and b2 down. Now we want them as a function of the orthonormal basis. So it is enough to replace this expression into that expression that you see over there. And you will come up with b1, which is equal to, sorry, b1 up which is equal to E1 hat minus E2 hat and B2 up, which is equal to square root of eta2, it. This is an equivalent, this is equivalent to what we see here above, but just expressed with respect to the orthonormal basis, but expressed in the orthonormal basis EI. That's a different way to visualize. Now it's clear that you see that vector B2 is a vector that has norm square root of 2, and it is oriented in the direction of eta2, as we found before. Now the representation in component with respect to the orthonormal basis is much easier. This vector here, the vector B2 up, is oriented as E2, but it has a norm which is square root of 2. And then you can see that B1 down is E1 minus E2, so it's something that is along this direction here. Very good. That was the second way to solve the problem. Algebraic is a little bit longer. You need to do algebra. You need to solve the systems of equations, but it is mechanical. You don't need to use your intuition, your creativity, just mechanical. You just need to know the properties of the objects and their definition clearly. There is a third way to solve this kind of problem that we are going to see it. Third way, third method, which is also powerful. It is algebraic in nature, but it is powerful. That is, we use what is called the metric matrix that I'm going to introduce you now. What is the metric matrix? What is it? The metric matrix. This beast here. That's very simple. When I give you the inner product between two vectors u and v, you know that each vector admits a representation on a basis, which is the component of u, that we call ui, with respect to the basis bi down, inner product vj with respect to the basis vector bj down. This is the inner product that we are calculating. Now you know that this is equal to ui, I throw it away out of the inner product operator, vj, and then we are left with bi, comma bj. This was possible because inner product is linear on the second argument, which implies that is conjugately linear in the first. So when I throw out this object here from the operational definition of the inner product, I, in practice, should take the complex conjugate here. But since the two vectors that we are considering are real vectors, which means that it's defined on a field of real numbers, the vector space, then ui up is equal to ui. There is no distinction between the complex conjugate and the number itself. So we have that uv is equal to ui up, vj up, and then I define this object, the metric matrix mij, which is defined as the inner product of bi, comma, bj. That's the definition of the object that we are looking for. It's a new definition that you need to learn. It's called the metric matrix. Why it is important? because it contains the rule to perform the dot product, the inner product. Instead of doing the inner product, once you know the metric matrix, you know how to do the inner product. No need anymore to calculate explicitly, element by element, the inner products. All the information that is in the inner product is simply contained in this object that we call the metric matrix. And whose definition is very simple. Take the basis, take the inner product of the basis vector, and that will be the metric matrix. Why it is important? First, it contains the rule, as we were saying, it contains the rule to perform, to calculate the inner product. Once I give you the metric matrix, I give you the rule for calculating inner products. Second reason is because it allows to rise or lower the indexes of a vector component. Let's see it. Let's see this. It's a very fundamental property. So let's number. This is property 1 and this is property 2. Let's see why. Let's say that I represent a vector v with respect to the dual basis. This representation of vector v with respect to the dual basis. Vi up. And then I ask you, what is Vi, the component? You know that by definition, we saw in class, the definition of the components of Vi with respect to the dual basis is simply given by the vector of the basis, this is the basis vector, inner product, the vector V. That's the definition. But this is equal to Bi, and here we have Vj, Bj, the components of vector V with respect to the basis, which is equal, I keep it going on, which is equal to Vj, the inner product is linear in the second argument, remember, that's Vj times Bi vector, comma, Bj. But that is what we just now define as metric matrix. So it is Mij Vj. This is our definition that we just gave of metric matrix. You see it here. Just before, we defined the metric matrix Mij as the inner product of the basis vector of the space, Bi, Bj. And so here, I'm using that definition to replace this inner product with the metric matrix. So at the end of the day, you have that Vi down is simply Mij Vj up. You see that we change the position of the index. Here we had the component of the vector V with respect to the basis. Here we have the component of V with respect to dual basis. Bi, and here we have the component of the same vector, the very same vector V with respect to the basis. Bi down. so more space, the basis bi down. So what is doing the metric matrix? It is lowering the index j up, and it is giving us the component vi down with the index down. It's changing the component of a vector, the component with respect to the basis into the component with respect to the dual basis. Okay? It is up to you to verify with a similar argument that vi up is given by mij vj. So in this case, we say that the object mij up is rising the index of j. You are summing over j, and what is left is an index I, which is up, as you see here in this representation. The question now, what is the relationship between mij, which is defined as bi bj, and that mij that you see with the index up and down, that it is defined as index bi up, bj up. What is the relationship between the two? That's what we need to discover. Are they the same object? Are they different? Let's see it. If I take the inner product of the vector u and v, we already saw that this is equal, we saw it just before, to mij down ui vj. You agree with me? This is what we found here. It is exactly this relationship that we wrote a few minutes ago. That was the defining relationship for the metric matrix. So I'm just rewriting what I wrote here minutes before. Now I'm using the property, which is the following. Oh, I don't see it here. It's written here. That mij, once it is hitting vj up, is giving me vi down. This is the relationship that I'm going to use. And equivalently, there is another relationship, which is vi up is equal to mij up times vj down. This is the second relationship that we are going to use. So here I will have that this is equal to mij, and then I have ui up, but instead of vj, I'm using the relationship that is written here. That is mj, let's call it k. Oh, no, j is good. mjk vk. See, I'm replacing this vj with this expression here because of that relationship that is written here. And this gives me mij times mjk times ui vk. This is the expression I hit with that replacement. But now I'm using here the property that I mentioned before as property star. I'm using this property here, the lowering of the index property. And so when this matrix hits this object here, I will have that this is equal to ui, and here you have vi down. Make sure that you understand that here I'm using the property that I call an asterisk, while here, for this equality, I use the property that I call two asterisk. This one, this is the rising, and the previous one was the lowering. So at the end, I have that this expression here that I have encircled in my box, indeed, needs to be equal to this expression here, which is encircled in this other box. But how is it possible that ui vi is equal to mij mjk ui vk? Is that true? Yes. If mij, it is equal to mjk, and both of that product, sorry, is equal to delta ik. That's the condition. Indeed, you can verify that delta ik hitting ui vk, it is equal to ui vi, which is exactly the expression that we need to match. That is left to you as a simple exercise about the use of the Kronecker delta. So in the end, we discover that the matrix M index up is the inverse, sorry, Mij index up, it is the inverse of the matrix Ij index down. They inverse relation. So remember, Mij is not the metric matrix. It is its inverse. That's the relationship between the two. Okay, I'm done with the introduction of this very fundamental object, which is called the metric matrix. Just remember, it is a way to calculate the scalar product. It is a way to change the up and down components of the vectors. And third, the Mij up matrix is not the metric matrix, but it is its inverse. So let's use this property to find the component of the vector bi. That was our original problem. Now the problem is very simple. We want to calculate bi up. That's our target. This is our goal. This is simply given as Mij up bj. I'm applying the property of rising and lowering the indexes of the metric matrix. This is the equation, the set of equations that we need to use in order to do that. So, first step is to calculate the metric matrix Mij. This is the first step. And we know that Mij is simply Bi, comma, Bj. I already give you Bi and Bj. They are unit vectors separated by 45 degrees. And so you will see that the metric matrix is simply 1 cos phi, 1. Okay, if you prefer, that is 1 over square root of 2. Okay, I have no space. Okay, leave it as it is. Now I need to calculate second step. Step number 2. Second step is to calculate its inverse. Its inverse, Mij up, which is the one that I need in this formula. You see, here is Mij up because I want to raise the index of Bj. Mij up is the inverse, so I just give you the formula because you are supposed to know how to inverse the matrix. This is with minus square root of 2 and 2. This is the inverse of this matrix that you have here. Watch out. Many silly errors that I see coming up during the partial exam, the midterm exam, or the final exam is that many students forget how to calculate the inverse of a simple matrix, even a 2 by 2 matrix. So make sure that you know how to calculate the inverse of a matrix. So we have everything that we need, and we know that the vector that we are looking for, Bi up, is simply given by that matrix. The vectors Bi up is simply given by the matrix Mij up. So times Bi times the vector Bj. This is equal to 2 minus square root of 2 minus square root of 2. And then we have B1 and B2. And this is given by the following vectors with the following component, 2B1 minus square root of 2B2. And here we have minus square root of 2B1 plus 2B2. And this is the answer of the problem. You see, one simple straight calculation using the metric matrix. This is the fastest method to solve the problem that we have. But it is the one that, you know, if you want to be fast, you need to know a little bit more in math. And the extra piece of information that you want to know and to master to get quick in your calculation in linear spaces is the metric matrix that allows you to be really performant in time calculations. So you can check that this is exactly the answer that we had before with the other method. So I'm going to find up. You see, this was the same answer, but calculated in a different way with the algebraic calculation. And we have now the same answer here, but in a different way. That's the fastest way. Now, let's get to question number 2, which is question number B in the exercise. I give you a vector V, which has component, vector V has component 1 and 2 with respect to, let me see here. Yeah. Now, there is an error. There is a typo in the exercise. It is written Bi down in the English version. That's not what I wanted to mean. I wanted Bi up. You see the correct exercise in the French version. The French version, the typo was corrected. So It's not with respect to the basis, but with respect to the dual basis. That's where the component is. Okay? So let's calculate the norm of this vector. What is the norm? That's the question. What is the norm of the vector v, which you see it is b1 up plus 2b2. What is its norm? And we know that the norm of a vector, it is induced by the scalar product. It is the square root of v inner product v. That's the definition of our norm. It is induced by the scalar product, and so it is norm induced by the scalar product, the dot product in our case, the dot product. And again, now I know how to calculate use the metric matrix. And this will be equal to mij vi vj. I hope you understand why. I repeat, I hope you understand why. I'm not using anymore the dot product. I have the metric matrix. I know what are the component vi and vj, because here I have my vector vi, which is expressed with respect to the basis bi. So I know what are the components vi and j down, which are x1 and 2. And so I simply need the metric matrix mij up in order to calculate this inner product. And it's easily done. I leave you the calculation, which is giving 10 minus 4 square root of 2. This is the answer, the norm of v. So go through this calculation. You already know what is mij up. It is mij up is this matrix here. I want you to understand how to do the summing here and to come up with the answer, which is the norm of the vector v. There was a final question, question C in the exercise, which was about calculating, determine the angle between the vector v and the vector b1, the basis vector b1. So again, this is a basic notion. The relationship, the angles between vectors are calculated using inner products. So we know that the angle between vector b1 and vector v is the inner product between b1 and b2, because that is the norm of b1. That is the norm of v times the cosine of the angle between the vector v and the angle b1, which is exactly what we are looking for. So the angle that we are searching is phi, will be the arc cosine of b1 comma v divided by the norms of b1 and the norms of v. That's the formula that you already know. So the norm of b1 is 1. The norm of b was calculated just in the exercise before, square root of 2. And then we need to understand what is this guy. What is this guy? It is the inner product of v times b1. So this is simply, as we saw in class and this morning in all these exercises, this is simply v1. The component v1 of our exercise. But we know what is the component V1 down. Okay, we gave it in the exercise before. The component V1 down was 1. So the solution to this exercise is simply phi is arc cos of 1 divided by 10 minus 4 square root. That's the solution of the problem. Okay, so we are done with this exercise. It was a little bit long because I wanted to give you many different ways, a review of the many different ways you can attack this kind of problems. Okay, so let's change exercise now and go to, let's see here, which exercise we can do. We can go to exercise 1.25. Let's go to 1.25. So again, I leave you 5 minutes so you see the text, and then we try to understand what is asked, and then we try to solve it together. So we have a change of basis problem. We are moving out the orthonormal basis, E1, and we are going to a new basis, BI. And I'm asking you to find the operator and its component. It's a matrix representation of the operator which is changing this basis. You know, the operator, that would be an operator that is moving the basis EI into the basis BI. Let's call it the operator R. This is called the change of basis operator, or the transition matrix, or the transition operator. Is a change of basis. So I'm asking you to find the representation, the matrix representation of this operator R. What is that matrix representation? So you see that we are moving out the orthonormal basis EI, and we are going into another basis BI, which is whose relationship with the original basis EI is given by this set of relationship of three equations. Now we know that the new basis BI will have a representation Bij with respect to AJ. And we know what is that representation. That's EJ. Okay, these are the components of vector Bi with respect to the, let's call it old basis, EI. But we know what are these components. We know them. We know that they are simply given by EJ up. Sorry, I wrote it in this way. Let's do it step by step. We are still on the first. That will be, there exists a vector that we call the functional EJ up, which is extracting the component out of the vector B. So that will be EJB. It is taking, sorry, BI, I call it BI. And then that will be EJ down. Remember, this is the functional that we call the linear functional that gives you the component of a vector with respect to the basis EJ down. We also know, I keep writing here, we also know, so I'm going out here, we also know that because of the Ries-Fréchet theorem, there is a unique dual basis EJ, comma BI, that is giving you that component. And let me call these Rij, Rji properly, times eta y, eta j. So I define here Rij, the representation that I'm looking for, which is exactly Ej times Bi. That's the definition. So the matrix that I'm looking for, the matrix Rji that I'm looking for is the matrix whose column are the component of the new basis Bi with respect to the old basis Ej. You see? Nothing new, everything already mastered. So let's calculate it, and that would be very easy, because now, this is an orthogonal basis, so remember, orthonormal, EI is equal to EI. This is the dual basis associated to the basis, the orthonormal basis EI down, but because we saw in class there is a fundamental relationship, an orthonormal basis, it is its own dual. which is what we see here in this relationship. There is no distinction between up and down indexes if the basis that we are considering, it is an orthonormal basis. The dual basis associated to the orthonormal basis, it is the orthonormal basis itself. So here, my Rji, it is equal by definition to Rji, which is given by Ej hat, Ei hat. And as you can prove, by doing that scalar product is simply 1, 2, 0, the component of the first vector. You see here, we have the components of the first vector B1, the new basis. The components with respect to the old basis are 1 and 2. And 0, because we are in three-dimensional space, so I put a 0 here. And then the component of the second vector, the second new basis vector, with respect to the 1 is 0, and this is 0, 0, 1. This is the matrix representation of the rotation, of the change of basis matrix. So we solved the first question. Now let's go to the second question, II, which is about calculating the coefficients of the metric matrix. Find the metric matrix Mij. Well, that's another easy exercise. Mij is by definition the product of Bi, the new basis, Bj. So take your time, do it at your place. You will see that this inner product is simply given by 5, 1, 0, 1, 2, 0, 0, 0, 1. And that's done. You simply need to take the scalar product between the basis vectors. So just as an example, M11 will be equal to B1, inner product B1, will be equal to E1 hat plus 2E2 hat, comma, E1 hat plus 2E2 hat. And that is, okay, you use the linearity, and then you will have that this is E1 hat, comma, E1 hat plus E1 hat, comma, 2E2. Sorry, let's write it in this way. Plus 2 E1 hat, comma, E2 plus blah, 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 blah. And then you will see that this is 1 plus 4, which is equal to 5. Do it at your place. I just sketch here the way you should do the calculation. Okay, let's get to the other question. Question number 3. Question now, it is find the inverse of the metric matrix. Find the inverse of the metric matrix. And that is simply, you know, the inverse of the metric matrix, Mij. It is simply indicated as Mij up. That's the notation that we use. Mij up is the inverse of the metric matrix. So Mij up will be equal to, do at your place, I just give you the solution, 2 minus 1, 0, minus 1, 5, 0, 0, 0, 9. So again, be sure to be able to invert matrix.
I was swimming with because she was too big. The last time I heard about it was that the little driver
Okay.
let her in his car because he said she was going to break it. But she filed a lawsuit for discrimination. Then went on the Breakfast Club, and when she didn't fit in any of the chairs, they had to bring a couch, which is not at all going to help her court case. The CEO from the Coldplay concert is still considering
we now
suing
go
the
to the
band
last
for the whole
question.
incident. Thinks he lost his job and his marriage. But like, are you going to sue someone for cheating on your wife? LeBron James is
We need to
also
find
the strangest lawsuit of all time. I guess the people that were making
determine the dual basis. BA up. Careful, typo. There is a typo in the English note. Is not it is written as BA down. This is not the convention for the dual. This is not the dual. Okay, so there is a typo. To be sure that everything is correctly understood, you go to the French lectures and you check on the French lectures because all these typos have been spotted out and corrected, as I told you in the class in the French version. So it's BA up that we need to calculate. So what's the way we want to go to calculate the dual basis now? We need to calculate the dual basis, and we have three methods. I told you one is geometrical, but that doesn't seem to be what you want to do because we are in 3 dimensions, and 3 dimensions, intuition start failing. So we could go algebraic, but that is a long pattern. Since we have already calculated the metric matrix and its inverse, it seems wise, it is wise to use method 3. So to use the metric matrix. The metric matrix. That's the fastest way. So I'll leave you 1 minute to think about how to write down the correct equations, and then I will do it. Let's go with the wise method. So we need to look for BI, and BI up will be simply Mij Bj down. That's the equation you need to write, okay? So we know exactly what is that. That is 1/9, 2 minus 1, 0, minus 1, 5, 0. And then it is 0, 0, 9. And that needs to multiply our vectors B1, B2, and B3. And this gives you the following matrix: 1/9, 2B1 minus B2, 1/9 minus B1 hat plus 5B2, and then we have B3. That's the final resolution of the problem. Okay, we are done also with this. So you see, this is wise because it's faster. All the rules to calculate the inner product are simply contained in the metric matrix. Let's go to another exercise, exercise 1.23. We go back a little bit and we now go to solve 1.23. Sorry, I leave you again the screen a little bit, so if you need to write, you have the screen ready. Okay, let's go to 1.23. Okay, this is a kind of an interesting exercise just for notation, because we're going to establish the link essentially between the notation that we use in physics in quantum mechanics with the notation that I introduced here, which is the one that is standard in the math environment. The math environment, we talk about vectors, and we say that vectors is called U. But in physics, we say that vector is a cat. So let's say that this is math, and this is physics, or quantum physics. It's not all physics, it's just when we go to quantum that we use this notation, quantum physics. Okay, and here in math, we have a functional u, which is associated to the vector u, functional, linear functional. And in physics, we call it a bra. This is a vector that belongs to a vector space V. This is a bra, is a functional that belongs to the dual space. Okay, they are not the same object, clearly. These are linear functionals. So the idea here is that I'm giving you a vector u in the physics notation, in the quantum physics notation, which is a cat, and I tell you that I decompose it on a basis, which is e minus I square root of 2, the basis e plus. Okay, just take the first one, and then we will do with the second one. Just concentrate on the first. This is a standard way you decompose on the cat basis, the cat vector u. And I'm telling you that the basis e minus and e plus is orthonormal. So in our notation, in the, let's call it math notation, math notations, we will call it, we will write u as ui ei, simply like that, where we have that ui are the components 1 over square root of 2 and minus I square root of 2. And then we have vector e1 hat, which is here e minus, and we have e2 down, which is e plus. Okay, this is the association. This is the standard way we write vectors in as linear combination of a basis with indexes, not plus, minus, cat, or whatever. This is the translation of the problem into our notational convention. So this is a vector space. We say that EI is a basis, an orthonormal basis of the space. H2. It is a Hilbert space with 2 dimensions. Okay, Hilbert. This is finite dimensional, so there is no distinction between pre-Hilbert space and Hilbert space. So this is a Hilbert space of spin of dimension 2. Dimension 2. So the problem here that I'm asking you is to calculate the functional. So I'm giving you the cat u, and I ask you, can you give me the functional u? What's the form of the functional, of the bra? A standard question in this kind of calculation between linear functionals and the basis, no? And we know from Riesz-Fleché, we know from Ries-Frechet theorem that to the vector u, it is associated a unique functional, linear functional to u that belongs to H2. Let's write it properly here. To a vector u that belongs to the space H2 is associated a unique linear functional u, it in something, that belongs to the dual space H2 star. And the association is very simple. Once u is u, that is simply doing u, comma u. That's Ries-Frechet theorem that we saw in class. That's the way we associate to u vector a unique linear functional via the inner product. It is the sense of the Ries-Frechet theorem. If you like the Dirac notation, this would be that u functional, the bra acting on the u cat, that would be the inner product of the cat u. Okay, this is the Dirac notation. The way you associate the linear functionals, the bra, to the vectors via the inner product. And that's because of the Ries-Frechet theorem. Okay, so our job now is to calculate u, or if you prefer, to calculate u that belongs to H2 star. That's very easy because we know that u, just to make sure that the notation is understood, I went a little bit fast on that, but it's standard notation. When I'm working with the math notation, I use the arrows. So this is u vector with an arrow, and I use the functional u, it in something, like here, with an arrow, and then the square brackets. When I'm working in quantum mechanics, I remove the arrows from the cat and the bra. So there are no arrows inside the cat and the bra, as you can see here, or you can see here, or you can see here, or you can see here. Okay, that's a little bit, again, of tricky notation. There are no arrows in the bracket notation. That's one of the advantages that we have in physics. But let's keep doing the transition from the math language into the physics one. So the linear functional that I call u bracket will be given by the component, as we saw in class, ui, and then some component ei of the basis A2. This is the basis of the dual space H2 star. Careful, watch out. It is not the dual basis of H2, which, by the way, will be EI. Okay? Here it is EI dot. It is taking brackets. It is a linear function. Okay? That must be really clear in your mind that we are working with this decomposition. We are working into the dual space and not in the original space. Okay. We need to understand what is this ui star, the components. If we want to have u, we need to calculate this component ui star, the component of the functional u into the basis of the dual space H2 star. We saw in class that that is simply given by u acting on the basis of H2, which was E happily. Okay, this is the definition of ui star. So it is the functional that we are looking for acting on the basis of H2. This is the basis of H2. So let's calculate it. We have that ui star, it is equal to u acting on ei hat, which, because of the Ries-Frechet theorem, will be u vector acting on inner product EI vector. But that is simply UJ EJ hat, comma, EI. I'm decomposing the vector U that you see here. I'm decomposing it into its component with respect to the basis of the H2 space. Sorry, here there is a parenthesis. I need to close that parenthesis. So let's go on with the calculation. Remember that in the axiomatic definition of the inner product is linear in the second argument. So it's conjugately linear in the first argument. So I have here U, comma, Uj, sorry, with the conjugation symbol above. This is complex conjugation. And why complex conjugation? Because we are in H2, which is not a Euclidean space. It is an Hermitian space because the inner product, it is defined on the field complex numbers. So here it is really fundamental, watch out, to remember that the inner product is linear in the second slot, not in the first one. And then you have that one needs to calculate the inner product of eta j, comma, eta I. But this is because of orthonormality. Orthonormal basis, that is simply uj delta ji, which is simply u hat I. You see here. Oops. U I. Now, you could have calculated this in an alternative way. Alternative way of doing